All right, so we're going to be learning about phase changes and the different phase change diagrams. This is a typical phase change diagram, okay? If we were to label this, and you need to draw this out on notebook paper, this is your solid, this is your liquid, and this is your gas. So you've got to be able to identify phases. So as you're going from a solid to a liquid, you're melting. As you're going from a liquid to a solid, you're freezing. As you go from a liquid to a gas, you're evaporating. You may also hear it called vaporizing. And as you go from the gas to a liquid, you're going through condensation. All right, one that is not shown, if I go straight from a solid to a gas, that is sublimation. And if I go from the gas to a solid, that is deposition. So you need to know all of your different phase changes. You also need to know the energy that is associated with each phase change. So if you'll notice, as I go from a solid to a liquid and then from a liquid to a gas, I'm having to input, so the amount of heat energy is increasing. Notice that also my particles are gone from being, tight to, by the time I get to a gas, they're very loose. So this would be an endothermic process, which is what we learned about last week. Okay. But if I go back and I go from the gas all the way to the solid, I'm going to be losing heat or giving off heat, not really losing it. Okay. And that is going to be exothermic because that heat, as it moves to the surrounding, is going to allow it to change from the gas to the liquid to finally the solid. So the reason why we have to go through this is later on this week, we're going to be discussing the amount of energy it takes from, if I'm down here at this solid, to how much energy it takes to go here. And we just learned about calculating specific heat. But you've got to realize that in a phase change, right here and right here, there's no temperature change, okay? This is constant. So in a phase change, you have no temperature increase or decrease, but you have energy increase or decrease. So if I'm going this way, if I'm going in this direction, I have more energy the closer I get to here, but my temperature hasn't changed. Your temperature will not change until all of that liquid has evaporated. Just like here, the temperature will not change until all of that liquid has melted, has frozen and turned to a solid. That's when you get a temperature change. So we're going to be calculating how to go from these different phases. And it's not that it's hard, it's just kind of a lengthy process. So that's a typical phase change diagram. The other one is what's called a triple point. Okay, this is a triple point graph. And with a triple point graph, the way this is always labeled, and I drew this myself so I could label stuff in here. This is always your solid. This is always your liquid phase. This is always your gas phase. Okay, so what I want to do is label some things here. This right here is what's called a triple point. And a triple point is where all three phases exist at the same time. Okay. Up here, you have what's called a critical point. And this is where it's such a high temperature and pressure, you can't really distinguish between the liquid and gas phase. So this line right here, this is a line of equilibrium between the solid and the liquid phase. So just like we did on that phase change, if I go this way, I'm going to melt. If I go this way, I'm going to freeze. Okay. This right here is the equilibrium line between the liquid and gas phase. So if I go this way, I'm going to evaporate. If I go this way, I'm going to condense. Well, you've also got to put into, you got to realize that there's this right here down here. So remember I talked about sublimation earlier. So if I go from this gas to the solid phase, it's deposition. And if I go from a solid directly to a gas, that is sublimation. That's typical. Think about dry ice. Dry ice is in a solid form, and it does not pass into the liquid. It automatically goes straight from solid to gas. So, some other things that you need to be able to do with this graph is you got to come up with the normal melting and normal boiling point. So, notice that I put pressure and I gave a unit of atmosphere. So let's put, all right, so our normal atmospheric pressure is right here at 1 atmosphere. All right, so if I want to know normal melting point, I'm going to look at where this solid line of equilibrium hits atmospheric pressure. And when I draw my line straight down, let's just say that this was 10 degrees Celsius. So my normal melting point is found by doing this, where atmospheric pressure and that line of equilibrium between solid and liquid meet. So it would make sense then that my normal boiling point would be the same thing. So my normal boiling point, here's atmospheric pressure, but this time I'm looking at where it meets this line of equilibrium from liquid to solid. And I would draw this down, and let's just say that this is 100 degrees Celsius. Okay, so this is my normal boiling point. So from a triple point graph, first you can be able to tell me how, what is the phase change that's going to take place. You need to be able to identify the normal melting point and normal boiling point. So I'm going to give you some examples. All right, I'm going to erase some of this stuff. All right, obviously I'm going to erase all of it because it's just being crazy. All right, so let's draw in another graph. So let's say that, all right, I'm going to do atmospheres again. So 0, 0.5, 1, 1.5, and this is my pressure in atmospheres. And I'm going to do temperature of -15, 0, 5, and then I'm going to skip to 115. Okay, so here's what we want to identify. Let's say that I'm this point right here, point X. What phase change is going to take place if I am now down here? So you got to look at what's going to happen. It's going to melt, then it's going to evaporate. So that would be the phase changes. Okay, I'm going to put it in a different way. What if I said that here's my point right here? Okay. What if I say that my pressure is increased to 1.5, but the temperature remains the same? This is in degrees Celsius. So that means here's